because I always forget to actually record it.
Yeah. So before we get started, I just wanted to.
First of all, thank you all for joining us.
These sessions are designed to be really nice and hands-on. So you all should have logins to our software. To our software. And it's a really good opportunity for you to try some
with the guidance of our team
as well. Apologies to those joining us from other states,
especially down south,
where
you probably hung around at school for an hour.
Before this kicked off at 3:30.
Nice and convenient
Queensland time.
Yeah. Again, thanks for joining us.
So just a few little ground rules before we get started. You've all done a great job. You've all muted yourself. We're all getting really good at this, which is great. Keep your video on if you can. It gives us a really good idea of how you're getting on, and if you've got questions, you can give us a wave. On the questions note, feel free to interrupt us. Just unmute yourself and yell. Questions. Otherwise, you can. We've got some questions. Otherwise, you can messages into the chat, and I'll messages into the chat as we go. I'll put it on my screen here. And if you're having any technical issues, once again, otherwise you've also got in your emails the phone number of one of my colleagues, and he will help you out if you're having any particular issues. Awesome. So yeah, before we get started, I wanted to cover a little bit about who we are. I know some of the know a little bit about on this call already know a little bit about some of Micromelon is and use them. Some of them I heard Harvey there talking before about their robots out. They've probably got their robots out. So I guess cool. So we started as two engineers from University of Queensland who ran UQ's, and through that what we found was there was a really big disconnect. The university was expecting of their engineering IT students, and what high schools were teaching and so as part of that program, we were heading into school running programs that were basically guiding students. Gifted students, talented students. But what we saw was there was a really big disconnect. So for these really people who already knew they wanted to do engineering, they got a really good taste of what. But for everybody else, it was. We started Micromelon Robotics in 2017 to basically combat that. So what we realized was that everyone needed a platform that was dead simple to use, that didn't have any little complexities, and really just absolutely frictionless way to start teaching in schools, whether that be high schools or primary schools. At the start of 2018, we revealed our Micromelon Rover, which is the virtual version of today. We're going to use the virtual version of, which is basically designed to be a single platform to draw the lines straight from primary school robotics in year 3 to first year university, without having to change platform over that time. In 2019, we began selling them into schools, running programs like this, running programs within schools. We now have over 1,200 of our robots in schools around Australia. To go along with that, what we also have is our Micromelon code editor, which is what we're using today to program our robots, which allows for Python programming and block-based programming in the same editor. So there's no need to change editors, no need to download a different program. It's all done within this Micromelon code editor. The other really useful part that we're using today, which was our little COVID project, is a full virtual environment for our rovers. So rather than needing a physical rover, as awesome as the physical rovers are, sometimes it's a lot easier just to not have them driving around the classroom, and that's where the Micromelon robot simulator comes really in handy. We can run all sorts of challenges, even ones that aren't possible in real life, within this virtual environment without having to build specific exercises each time, and also without needing to invest in mazes and sumo boards and all sorts of other equipment that you might need to complete some of these challenges. The newest little addition to the Micromelon family is MakerHero. So MakerHero was a company that we acquired at the start of the year because we were dealing with so many schools having problems with their 3D printers, and a lot of that came down to either cheap material or printers that weren't maintained, and so we ended up with MakerHero basically as our answer to 3D printing in schools. So we have really high quality, affordable materials, but we also offer service plans and training, and so one of our next sessions like this will actually be on 3D printing.
So before we dive in, it's really useful for me, and it's probably really useful for everyone else on the call to know where everyone's from. I know we've got people coming from all around Australia on this call, and so it'd be great if those who are willing to unmute themselves and give a little intro of where they're from, what you're teaching, and what you're currently using in the classroom. So does anyone want to kick us off?
I'll kick off if you like.
It wasn't. That's not how it's intended, but how some people might interpret it, right? No, I would be like, okay, so who in this room do you think is the average?
Apparently, I was the closest to the average person.
Okay.
Anyone want to kick us off with an intro?
Wow.
Hi, my name's Nicole O'Neill. I'm from Yeppoon State Nationalist College.
Is it all supposed to be awkward, or is he?
We all good?
Yeah. All good.
And we've been using MakeCode for the past year and a half, or a year now. We're in our third semester of it for our Year 7 and 8 program. We're looking at buying our first set of robots, and as someone who has investigated the virtual robotic world to deal with not having enough sets in a high school classroom, which can be problematic,
Yep.
I will say hands down a very good program. Very few issues. The girls are getting it quite well. I'm teaching at a girls' school, and we're finding they're really engaged.
No, that's great. That's great to hear. Thank you very much. Anyone else want to jump in? We've got a few come through on the chat. We've got another one from Yeppoon. We've got Narang State High School.
Hi.
Yep.
Hi, Jeff Corcoran here, CQU Mackay, teaching autonomous technology.
No.
Cert 2 in high schools.
No, thank you very much. We've also got, so Rockhampton State High in here. We've got St Margaret's Mary's in Townsville. These EQ usernames are really hard for me to work out what the names are. We've also got Ormiston College. Awesome. Thank you very much, guys. So I guess the objectives of today's sessions are to obviously cover a little bit about the Micromelon rovers, the Micromelon rover platform, but the intention here is really for you guys to be able to go away and keep playing with this. So all the accounts that we've created for you will remain active for a month after the session, but we also want to give you insights into how these activities can be structured for all student year levels and skill levels. So obviously this session didn't have a restriction on primary schools or high schools, or we've even got universities in here, and so what we really try and harp on about a little bit is that the platform is great for all the way from year 3 all the way up to university. We also want to give you all a little bit of confidence in how to guide students through a number of activities from our online resource library, which is ever growing. There's over 50 activities there that you can run in the classroom with the rovers and with the simulator. But we also want you to understand and have a bit of practical experience programming with the Micromelon code editor, as well as a little bit of Python. So we will touch on a few Python concepts in here as well. But I also have a little case study that we'll talk about at the end, which is really useful. So what we're doing today, so we've just done a little bit of an intro on our setup. We're then going to jump straight into doing a little activity with the Micromelon simulator and the code editor. We'll then do a little Python crash course, 15 minutes. I promise it's not too detailed. We'll start using a little bit of branching iteration with our seesaw challenge. I'll run through a little case study, and then we'll have a go at some line following at the end. Then we'll have a little bit of time at the end for some questions and discussions around what we've learned throughout the day. So in an email that all got sent out to you, you should all have an account. So just to quickly, we can do thumbs ups in chat. Is anyone going to run along with this? So if you got the code editor and the simulator installed, and is there anyone who hasn't who wants to do that? Because I can give you a little bit of time to do that now. Cool, we got a few people installed. Awesome. Okay, cool. Sometimes no one's got it installed, and then it just changes what I do. But if we've got someone here who are installed who are going to run along, then I will run it like that. So the first activity that we do is not really an activity. It's just about getting our editor and our simulator attached to each other, as well as making sure that everything's working for us. So I'm going to switch over to our editors here, and so you can see that on the left-hand side here I've got our Micromelon robot simulator. On the right-hand side I've got the code editor. So if you've got this at home, you should end up on this screen and also this screen. Can be really useful to split them side by side like this because they are two separate programs. But what you'll see as we go through, sometimes it's easier to not do that. Sometimes it's easier to just have the simulator in the background, write your code, and then jump back. The most important thing, and this is all covered in our blog post that we've got on our website called Getting Started with the Robot Simulator, is actually getting these things to talk to each other. And so you'll see up in the top right-hand side of the code editor here, I've got this connection area. And for the real robots, and I'll show you this on camera, for the real robots, what you get on the screen is this 4-digit number. So on this one, it's 0711. So I can type that number up there, 0711, you see that, hit connect, and you'll see now, again on camera, my robot is now connected. Because not all of us have physical robots here, what we want to do is actually connect to our virtual rover over here. And so we've got this rover here sitting in the free space activity, which I'll touch on in a second. But we can also see here we've got our robot ID up in the top right hand corner. So for this robot, this virtual robot that doesn't exist, I've got robot ID of 9000. And so now straight away we've got now our run button up in the simulator as well as our run button active in our code editor. So now any little block that we want to drag in, so say we jump into movement and we say move forward 10 centimeters, we can jump in here, we can either click run code in our code editor or we can press the little play button over in our simulator. No matter which one we press, they do the same thing, and now our program has run and finished. This program's not very long. So this is sort of the basics of how the flow for students works here. So each student is writing their program in the code editor, pressing run, whether it be in the editor or in the simulator, watching their program happen, back to the code editor, a little bit more tinkering. And so what they end up with is some nice long pieces of code in here, but also a way to do this without needing a physical robot and without having to worry about robots going flat or falling off the table or anything like that, because it's all in this virtual environment. Awesome. So I've also just accidentally then covered the basics of sort of some of these challenges. So for example here, what we've got in our editor is we've got a whole heap of different challenges that you can do, and the one that we're going to start with is this free space activity. So you can see in here that we've got a nice big area with walls around the outside, and we've actually got a circle here that we can use our color sensors on our robots if we really want to. The first activity though that we almost always run with students is this activity called driving shapes. I'm going to jump back to this and this is straight off our website. So this is our driving shapes activity. Basically it's make our robot drive in a square. So it says here, learn to make your robot move and draw shapes with it. Start by making the robot drive in a square and then a triangle, and then we can move on to some more complex concepts like loops and other shapes like hexagons and octagons. For each of these little activities, we've also got relevant coding skills. So in this case, we're teaching iteration, but also relevant rover concepts or relevant parts of the rover that we're using. And so in this case, what we're using is our motors. And what can be really helpful with these, I mean, this one's reasonably simple, is this exercise setup area as well. So it tells you you need a flat uniform surface to drive on. When these get more complex, they actually detail out, like here's how you're going to build your maze, here's how far apart the blocks need to be. But that can be really helpful to just grab one of those and run that in a session and go from there. So for those that are playing along at home, I'm going to give you a hint. These are the two blocks you're going to need to do this driving shapes activity if you hadn't already worked that out. I'm going to run through it slowly, and so hopefully you'll be faster than I am, so I'm not necessarily giving you the answer straight away. But we'll jump back over and we'll have a go at this driving shapes activity. So I've already put this block in here that says move forward 10 centimeters. And what you'll see is that as I've done this has generated a line of Python code on the right hand side. And so already this move forward 10 centimeters is represented over on the Python side with a motors.move distance. Down on the left-hand side, like most other block programming pieces of software, you'll also have all your different blocks that you can use. So we call this the block library or the block catalog. For this one, I've already given you the hint in the presentation that the one that we need is going to be turn left by 90 degrees. So I've grabbed this one here. But what you'll see in there, there are a whole heap of different options. The trap for young players in here, and the trap for students quite often, is these top two blocks. The first one here just says move forward at speed 15. And what that's saying is just set the motors to 15 speed and then move on with the program. And so what happens if I put just that block in, if I put that block in and I leave the rest alone, what you'll see over here when I run the simulator is that the rover doesn't move. Because what's happening is the rover is having its motors set to speed 15, which is 15 centimeters per second, but then immediately the program's ending. Whereas these other ones that we've got here, like move forward 10 centimeters, are going to move a fixed distance regardless. And you see how when the program is running, each block that is operating is lit up. So when I run this one that's move forward and then turn left, I see the move forward is lit up and then the turn left is lit up. That can be a really useful step for students, especially once we get into loops, especially when we get into more complex programs, to see which line of code is currently running. Because as you see, if I set this to 1,000 centimeters, we spend a lot of time in this block because we're here waiting for 1,000 centimeters to happen. And so if the next thing in your code is if the ultrasonic sensor sees something, then you're never going to get there. You'll eventually get there, but it'll take a long time to get there. So for this one, we're going to do a 10 centimeter square. Now, what we can do, and one of the options for this challenge is to do something like this. And we'll go two more. We'll reset our rover, hit run, and so now we've got our rover that is driving in a square. Done. And see our rover basically came back to the same spot on the ground. Slightly different, and there's a reason for that. The reason for that is that our simulator is a physics simulation, and so therefore there are little effects that happen with the real rovers, like the floor being slightly dusty or non-uniform or bumpy or whatever. We also simulate that in our robot simulator. So what we try and do is make sure that the robot simulator represents as close as possible to the physical robots that we use in the classroom as we can. And so you see the physical robots are going to have a little bit of drift, and the virtual robot also has that little bit of drift. The reason I really like this as a first activity is because it allows us to benchmark students, I guess, on where they're at. So you'll always have some students who have already done some of this sort of programming before, and so they will immediately jump to the more complex and nicer solution, which is to use an additional block in here called a loop. And so we can drag this one in that says repeat, and that's just basically going to give us exactly the same result. We're going to drive in a square, like so, and that's basically, we've got exactly the same program. Again, see, because we've run that over the top, we've now moved out by the same amount again, so our little drift that we've got in our robot has happened now twice. What's really useful though is that you're going to now see that students who pull this in have already done some of this before. So rather than having to go, alright everyone, if you've done a scratch before, put your hand up, and half of them lie to you, you can say, alright, go and do this challenge, and now we know, alright, we've got some students who are going to do this. You'll also get some students who try and write a function that can do any shape. Because the next thing that I always say is, okay, now make it do a triangle. And so some students will go in here and do this, and they'll have their triangle. And some students will see the next thing coming is, okay, now do a hexagon, and they will write something generic that they can change one number, and their whole program will populate through. Awesome. So as I just sort of covered, we've got this option of using loops, and I also sort of covered this as well, where we've got in our code editor this Python generating as we go. And so on that right hand side of the Python, we saw this line of code right at the start, which is motors.moveDistance 10. And so in Python, what this is basically representing is the motors here in red is the class, which in our case is which part of the robot we want to talk to or we're asking for. we've got our function, which is our actual action, which we call the instruction or the call. And then in this case, we actually have an argument. So we're not just saying move distance nothing. We're saying there's actually an attribute here that we need to add, and that's here is the argument. So we've got this here. And so you'll see here in our version with the loop, we've got exactly the same here for our turn. So we're still talking to the motors. We then have turn degrees 90 or negative 90, and so in this case, negative 90 is saying 90 degrees to the left. Now, what we also covered there was, really quickly, we covered the concept of a repeat loop. And so we were saying repeat the same thing 4 times. What can also be really useful is to have a loop that goes forever. And so my example I always use when I'm talking about this is your teapot or your kettle at home. Regardless of what temperature the water is when you start the kettle, it needs to boil. So if we fill it with ice cubes, it's going to take a lot longer. If we've just boiled it, it's already been boiled, and we boil it again, it says it's done within a few seconds. And so what we need is for our robot or our kettle to know when the water has hit a certain temperature. And there's no possible way for us to know that at the beginning of our program. So we can't go in here and change our repeat to say, all right, it's ice, repeat 1,000 times. We have to just do that on the fly. We've got to work out when it gets to that point and then finish our program. And so what can be really useful, and we use this a lot in robotics and a lot in automation, is the notion of an infinite loop. So a loop that never ends and just keeps checking, keeps running the same thing over and over and over again. And so in this case, what we've got is while 1, keep on swimming. So we're just going to we're just going to print keep on swimming forever and ever and ever and ever and ever. What we can do though, where it says 1, because 1 in programming just means true or yes. Just going to quickly, yep. What we can do in here is add a question for our robot, and we can say while the temperature of the water is less than 100 degrees, or while the robot isn't crashing into something, and we can add that in there so that our program has value that it's looking for before it finishes the program, or before it moves on to the next thing even. The other thing that's important here, especially with our rovers, is when we're using an infinite loop, it's really important to explain to students that the run stop button exists. Rather than them having to run after it and try and find it when it's driving off into the distance, they can just hit the stop button in the editor. And so you can do the same in the simulator. You can just press stop, and I'll show you that in a second in the editor. So I just talked about the notion of asking our robots a question. And so obviously we've made our program now drive in a square or a triangle, but it does that no matter what our inputs are, no matter where the robot is, no matter what surface the robot's on, no matter what happens. So if there's something in front, if we start it right next to a wall, it's going to run into the wall. If we start it right next to the edge of our desk, it's going to drive off the edge of the desk. And so what we need to be able to do is ask our robot different sorts of questions. And so the block and the programming concept that we want to use for that is called an if statement. In this case, what we're asking our robot is if the ultrasonic distance sensor, which is the little sensor on the front of our robots that shows how far away something is in front of the robot, is less than 10. 10's in centimeters. So we're saying if the ultrasonic distance sensor is less than 10, we print hello. So basically, if there's something in front of us, say hello to it. What we can also do though is chain these. So this little settings cog that we've got in our block here for the if statement, we can chain this. So we can say if one thing is the case, otherwise something else. Or we can say if one thing is the case, if another thing is the case, otherwise something else. And so we can chain these in to get more complex programs. So we're going to do one of those now. So one of the really cool activities that we like to do is this one here called the Balanced Waters Seesaw. And the reason it's really cool is our robots have a sensor called an accelerometer. The accelerometer is the same sensor that your mobile phone has for determining whether your phone is in landscape or portrait mode. And so when you open a YouTube video and it goes sideways, this sensor is how your phone knows what to do. Basically how this accelerometer works though is it's sensing where gravity is in relation to the robot. And so it's easier to explain this with a real robot. And so with our robot here, we've got gravity coming straight down on it. So if I drop this robot, it's going to fall. Gravity is pointing straight down on it. And so what the accelerometer can do is sense where gravity is in relation to the robot. So if the robot is upside down, it will know that the gravity force on our robot is pointing in this direction now in relation to the robot, which is actually up in its normal orientation. But it can be really useful. It's not that restrictive, so we can actually see if our robot's on an incline or a decline. And so if it's on this sort of angle here, we can see that it's driving uphill. If it's like this, we can see that it's driving downhill. A really useful thing that we can do is connect to our robot. So I'm just going to switch over this one. And so I've got my robot here. And this rover button up here next to the where we can name our robot will actually show us all of the sensors on the robot in real time. And so we can see that there's nothing in front of it because there's empty space out to that side next to me. If I put my hand in front, you'll see the ultrasonic sensor here. On the front of the robot is seeing something very close in front of it. You'll see that our colour sensors are kind of not seeing a whole lot because it's seeing my hand underneath quite often, or my shirt or whatever. But you can see down here we've got our accelerometer, our gyroscope, and our accumulator gyroscope. And so right now we can see that the z-axis of the robot, which is up and down, is experiencing 1g of force, which is gravity. We're experiencing 1g of force that way. If I really quickly move my robot up, you'll see that that goes to a smaller number. If I drop my robot, you'll see that goes to freefall. So we're moving with gravity now, and so we get a number. If I let this robot drop and hit the floor, it would hit 0, and then it would hit a much bigger number as it hit the floor. But what's useful is that we can see that gravity vector gets distributed amongst the other axes as I tip it. So you see there the x value, as the robot's facing upwards, is 0.5. If I face the robot downwards, that x value goes to negative 0.5. And so this is a really useful little sensor because we can determine if our robot's trying to go up something, or also if it's running into something and trying to drive up the wall. But we can also see if we're going down. So if we're falling down a hill or about to go off the edge of the table. If we got a table there, we can see the robot's about to teeter off the edge. I wouldn't recommend that one. I've tried that one in the classroom once, and we ended up with all the robots on the floor. So yeah, this can be really useful. So what we're going to do now is we're going to write a little program that solves our seesaw challenge. And so on the, I don't have it there, on the simulator here, we've got, in the exercises, we've got this one here. And so this is our seesaw challenge. For each of these simulator challenges in our robot simulator, you can also, and my camera is actually hiding it, move to the other side for a second, you can see we've got camera controls down here. So these camera controls actually show us and allow us to switch for different locations for our camera on the robot. So we can get a top-down view, we can look directly behind, but for every single one of these activities there is also an exercise-specific view. So this is a really useful view for the seesaw because we can see when our robot gets to the middle and starts tipping off. What you'll also see on each of these challenges is you've got this little blueprint, which is the instructions on how to do this challenge. So you see here, balance your robot at the center of the seesaw, tips, use the accelerometer and gyroscope. And so if I just enable keyboard controls quickly, we can see that on this challenge, our robot's going to look like it's going uphill, and then eventually it's going to hit this little region of our seesaw where it's going to tip the other way. The whole point of this challenge is to find the region where the seesaw is perfectly horizontal. And so we'll get somewhere like that. And what you'll see is that these little blue lines on the outside go really dim when you're not horizontal, but the closer you get to being horizontal, the better. So, what we're trying to do here is ask our robot a question about this accelerometer sensor. So I'm just going to switch me back over here. So we're going to jump back to our editor. Jump back to the editor. I'm just going to create a new project. We'll call this one Seesaw. Seesaw 2, I've already got one apparently. And so the first thing we're going to have to do is drag in our infinite loop. So in this case, we have got exactly the situation I explained before with the kettle. We don't know how long it'll take us to get to the middle. We just want to get there. And in this case, if we actually overshoot, we want to be able to come back. So we want to constantly sit in that middle position. For example, if a robot comes up behind us and bumps us out of the way, we want to get back. So we're going to drag in this infinite loop. So it's going to say repeat while true. And then we're going to ask our robot a question. So we're going to ask it about the accelerometer. Now, I just want to think through how this is going to work. So when the robot is on an inclined plane, we want to drive forward. When the robot is on a declined plane, like this, we want to drive backwards. And so that is basically our if statement. We're going to say if robot is pointing up, drive forward, otherwise drive backwards. In the editor here, we've got all of our sensors here in the sensors category. And in this case, what we need is the accelerometer. And so we're going to drag that into this first 10 position in the editor there. And so now our line of code reads, if read the x-axis from the accelerometer is less than 10. As we just saw, 10 is probably not the right number here. What we're seeing, now we're on the declining plane here, we're seeing, I'm connected to my real robot, which is on the desk. Like that. We're seeing that we're getting negative 0.23 on the decline. And so we really want if our robot is greater than, our accelerometer x-axis is greater than 0. If it's greater than 0, so we're on the inclined plane, we're going to move forward. And this is where these top two blocks I mentioned before that are a bit tricky are really useful, because these aren't moving forward at a set distance. These are just setting the motors to a speed. Then what we want to do, we want an else. So we want to, if that isn't the case, we also then want to do something else. So we're going to jump in here, we're going to grab our else, like this, and I'm just going to use Control-C, Control-V to copy this block out, and we're going to set this to backwards. So this is our whole program that we're going to test here now. If the accelerometer is less than 0, move forward, otherwise move backwards. Do something else. So we're going to jump in here, we're going to grab our else, like this, and I'm just going to use Control-C, Control-V to copy this block out. Awesome. And we're going to set this to backwards. So this is our whole program that we're going to test here now. If the accelerometer is less than 0, move forward, otherwise move backwards. So what we probably want here is something that isn't 0. So 0 is probably not the best answer. We're going to go 0.1. Awesome. What have I done wrong? Apparently we're not. Our robot is on the flat at the start. So what we probably want here is something that isn't 0. So 0 is probably not the best answer. We're going to go 0.1. I'm going to debug this the way that I just showed everyone we should debug this. So notice here that as the robot is moving, we're getting this number jumping all over the place. So that X number is going positive and negative as we're moving. So what it probably means is we're just moving a little bit too fast. I'm going to debug this sensor to be useful the way that I just showed everyone we should debug. So let's decrease that speed. So notice here that as the robot is moving, we're getting this number jumping all over the place. So that X number is going positive and negative as we're moving. So what it probably means is we're just moving a little bit too fast for that sensor to be useful while we're running. So let's decrease that speed. Okay, so now our robot's going to slowly move up. We're going to get up to this region here where we are expecting our seesaw to tip. Have I got this the wrong way around? I think I do. Yes, I do it the wrong way around. Whoops. And as it tips, we're going to move backwards. Okay, so now our robot's going to slowly move up. It's eventually going to get up to this region here where we are expecting our seesaw to tip. What might be useful is to go even slower. But what also might be useful is something a little bit more complex, where we're actually using that value to determine how fast we're going. And as it tips, we're going to move backwards. And so what we see, if I start it, so now we've got a robot here, it's eventually get up there and it'll just do that. We've got this bit of an oscillation happening. What might be useful is to go even slower. What we also have is a version of this that is even more complex. So we have a version complex where we're actually using that value to determine how fast we're going. We call the balance board, which is the 3D version. And so the tricky part with this is that you've got to actually plunge. It'll get up there and it'll just do that oscillation. If you just sit on the top here, you're just going to move back and forth because it's perfectly level. What we also have is a version of this that is even more complex. So we have a version of the balance board here that we call, the seesaw that we call the balance board, which is the, but because this thing moves in 3 dimensions, we've also then got to take into account left and right. And so you'll see this will just oscillate here, but it won't actually ever fully balance. Awesome. So Yeah, that's our seesaw. So that's a really basic overview of how we can use our sensors to do something a little bit more complex. And so, as I said at the start, we try and make these activities work for all different year levels. And for this one, I wanted to break this down a little bit. The easy version is obviously what we just did. So we can do that. We can also then make it even easier. So we're having really young students. We can move our robot to be already on the seesaw. If we want to make it a little bit harder, we can make them start on the flat. So they've actually got to enter the challenge themselves. And then the challenge version, the really hard version, is making something that can balance the 3D version of the seesaw as well. Awesome. Did we have any questions thus far? I realise it's a lot of information, but if there's any questions, feel free to jump in. Otherwise, I'll keep moving.
I see you've got microbits there. Is that something you also support?
No, so the microbits is the next little bit. So this is a little case study that we've got that I'll go through in just a second.
Okay.
I'll cover why the microbits there.
And the second bit, I saw that you had some claws on the micromelons. Is that something you can print? You can actually like print, or do you have to buy them?
No. So all of those attachments are actually available. And this is a good opportunity to have a look at this. So this is on our website. We've got all these attachments that you can either print yourself or you can buy them from us. You haven't got printers. And these are all designed by our team and designed to use off-the-shelf parts. So you can buy the servo motors from JCar or Core Electronics or anything like that. And all of the fixings, like all the screws, all the bolts, anything you need for that are available from somewhere like Bunnings. So they're all reasonably simple. You can download these today and just print them out yourself. But we do offer a printing service for them as well on our website. We've also just had the question through of, is there a way for teachers to see the students' programs remotely? Which is an awesome question. I'm going to jump back here. So, yes, there is. So in our code editor, we have, when you log in as a teacher, so you all at the moment have student accounts, except for a few who are at schools already using it. And so I'm logged in as a teacher. I can jump in and actually see everyone in this session's login, but I can then also go in and have a look at all of the students' programs. So I can go in here and look at a session that we ran at a school here in Queensland and actually go in here and have a look at their programs. So for obvious reasons, this is really useful. If a student sends you an email and says, I've got this program that doesn't work, you can jump in and just have a look without them having to screenshot it or save it to you or anything like that. But it can also be, the other thing that can be really useful is to jump in here, something like this seesaw activity. I can then send this out to the entire class. So I can actually send this out to all of the people in this session because I've created you as a class. And so now you should all, if you're logged in, you'll get this Seesaw 2 activity, my answer to it, will pop through into your editor. And so this can be really useful because we can jump in here and we can create a little example that says, this is your assignment. We can go and put in some broken code. And we can ask them to fix it. Or we can send someone's solution down to everybody. Or what I really like using it for is being able to jump in and show the entire class someone's pretty neat solution to a problem on the projector or on Teams or whatever. And so you can jump in and have a look at those solutions. I won't pull anyone from the sessions up. But yeah, super useful feature. You've also in there got the ability to disable all the robots in a class, mute all the robots so you can disable the buzzers. We can hide their screens, and so they'll actually blank the screen off. It shows a little message that says you should watch your teacher. But the other thing that's really useful is you can lock students to either a block view only, a text view only, or you can lock them to this hybrid view, but only let them see one side. And so you only then see, only edit one side. So rather than being able to come in here and fall back on the blocks, you can make students see the blocks but have to write all their code in Python? Yeah, great question. That one. Yeah, so this one is a little case study of a school up here in Queensland who started using Micromelon Rovers. They were one of our very first schools way back in 2018. And the way that they used them was a really, really interesting use case that I still find really interesting how they did it. So they had they basically had a unit of programming where they wanted to get students using a whole heap of different platforms. So rather than just doing 20 weeks of Lego or 20 weeks of Micromelon or 20 weeks of Microbit, they wanted to split this up. It also helped them because they had limited resources, so they could have half the class working on one, half the class working on another. And so basically what they were asked to do is find out, they did sort of 5 or 6 weeks of work on each platform, and then they got asked to write a report on each platform, basically comparing them all against each other. And so what they worked out was that the little Lego EV3 arms they built were really great at pick and place operations, so grabbing something and putting it somewhere else. The Micromelon Rovers were really good because they had tank tracks and could carry a lot of weight because they're quite torquey. And the Microbits were great because they were easy to program and had sensors and lights. And so then they had to come up with a challenge, basically, that they could all participate in with all the different platforms all at the same time. So rather than having 3 fields built, one for Micromelon, one for Lego, one for Microbit, they wanted all of these platforms to sort of work together. And what they came up with was this program called Hungry Microbit. And so what they had was the Lego arms here were placing something on top of the Micromelon robots. In this case, it was a little Lego wheel. But the whole application here was that these were deliveries being sent out to houses around the suburb or whatever it is. Then the Micromelon robot had to navigate along these coloured lines. So you've got a red, a red, a blue, and a yellow line. But the Micromelon rotors, using their colour sensors on the bottom, had to navigate through this field. Then when they got to the end, they had the Microbits on a cup, which could sense the tilt and sense the motion of the Micromelon robot coming over and depositing that shipment or parcel or whatever it is to the house. And then the Microbit would actually show a little smiley face when its parcel arrived. What was also really cool in this, though, is they had 2 students in that grade who just weren't interested at all. And they decided what they wanted to do was just be a little bit of a menace and have some additional Lego robots roaming around, basically sabotaging the deliveries. And so this black line that you see here is actually the sabotage line, or something they called it like that, where the rovers were just doing laps, and what it meant, it just added a little bit more complexity for the Micromelon rovers to also use their distance sensors on the front to make sure they didn't crash into the Lego robots. And so these 2 students who really weren't interested, didn't want to do any robotics, ended up doing a lot of robotics and actually doing probably more programming than most other people because they were just trying to get in the way, basically. So it's a really good little example of how you can use multiple things, get different students engaged in different things, but all for a common cause, which is great. So the core part of this challenge that was in that case study was basically following this coloured line. And so the Micromelon rovers have got 3 colour sensors on the bottom, which is really useful because we can then do multiple sensing of a line. Rather than just having a single sensor that has to detect the edge of the line, we can actually detect the centre of the line, because we can be looking at when the left or right sensor fall off the line, and then we know which way to come back. So basically the way these colour sensors work, if you haven't used a colour sensor before, is it shines, in our case, it shines white light onto the surface. And so what happens there, and it's colour theory that we quite often teach in science at schools, is we shine white light onto red paper, and only red light comes back, or most of the red light comes back. And so then that red light that bounces back is detected by the colour sensor portion of the sensor. So this is actually detecting different colour wavelengths of photons hitting a sensor element, and then the white light is helping to basically create more of those photons to sense. And obviously the Micromelon rovers have 3 of these sensors spaced out, so we can actually detect 3 different colours at a time. but also detect when one of these isn't a colour, so when it's just white, like it quite often is in these challenges that we run on a map like that. So, in our simulator, we have a challenge here called line following here, and so this is our line following course. So this line following course is based off one of the RoboCup line following courses from a few years ago. It conforms to all the standard line following rules for RoboCup and RoboRave, except that we've got the turntable here, which is a RoboCup only feature, where we have to detect the little red element here and determine whether we go the short way or the long way around our turntable. Awesome. So I'm going to create another little project here, and I'm going to have a look straight away at our robot sensors. There we go. Alright, so what we see here is we've got our 3 sensors, and it'll actually give us a little preview of what colour they're currently seeing. So, makes sense. On this one we're seeing, on the left we're seeing green, middle we're seeing white, on the right we're seeing green, which means we're pretty central on our line. What you're also getting here is a whole heap of different values from our sensor. So we're seeing the red, green and blue amount of photons that are coming back, as well as the overall brightness of what's coming back. So you'll see that for a white light, we're actually maxing out the sensor. We're hitting 255, the maximum number that this sensor can read. And for the other sides, we're getting a smaller number. So we can immediately see here a few ways that we can use these sensor values to achieve our intended result. And so in this case, I'm going to go for the simple approach. So a little bit of a common trend, we're going to pull in our infinite loop. We're going to pull in a if-else, because I already know we're going to need at least a few elements to this. And in the sensors category, we have this nice easy block that basically says, is the middle color sensor red? And so what this is going to do is, instead of giving us one of these numbers that we're seeing, this is actually going to return a yes or a no or a boolean. And so we can put in here, if the middle color sensor is white, if the middle color sensor is white, what we want to do is move forward, and we are going to move forward just like we experienced in the other one, quite slowly. Now we've got a few other questions we want to ask here. If we just run this code as it is, and let's for example say if it's not white, we just stop. So we'll run our program, we're going to hit this first corner here, and our robot's going to stop, and our program's just saying we've stopped. When we get to this case here, and so this is great because we can pull up our sensors again, we see that the right sensor is now seeing white. So this right sensor is seeing that the white line is now under it, which means we need to move to the right. We can jump in, we can drag an else if in, which allows us to ask the robot an additional question. We can copy our middle sensor and change that to the right sensor. And when the right sensor is white, we're going to set our motors to turn right slowly. Alright, so let's run that bit of code now. We start turning right, and you can see here as it lights up, splitting between the two. Alas, we have hit a left turn. So we now need to replicate that again for our left turn. We can drag this in. We can do what I just did before, we can copy this one. We know that we're going to need this one as well. We can change these two to left. And now we're going to get a program that will at least make it around the first and second turn. And so as you see, it's really useful here to be able to see which part of the code is running. So we can now see, alright, we're getting right turns occasionally, we're getting right turns occasionally. When we get on the straight section, you'll see that only the move forward lights up. So we see that that's working really well. We get here, now we start doing a left turn. And so you can see that the left turn here is lighting up, and the left turn in the blocks is lighting up as well. Super useful. Now as we get through these turns, some of these turns get tighter. So you can see these last two before the roundabout are much lower radius turns. So these are going to be trickier for our algorithm or a little bit of program here to navigate around. Let's see how it goes. The other useful thing we can do in here is actually jump into our editor, so we can actually see our rover editor here. We can see what the actual sensors are seeing. So you can see the accelerometer's moving around. We haven't got any distance sensor stuff happening, and we now see that we've stopped. So we're hitting this stop block here because we didn't make it around this bend. Now, a really simple tactic we can do here is, instead of when we see nothing stopping, we can just do nothing. So rather than stopping, we just don't do anything. Because if we don't do anything, it will continue to do the last thing that it saw. In this case, the last thing that it was doing was trying to turn left. It just didn't quite turn left quick enough. So what we can do for now is just drag this one out. What I'm going to do is make it so that we don't have to go and watch that all happen again. And I am going to untick this reset rover on play. I'm going to tick keyboard controls. I'm going to drive our rover back a little bit, and then we can actually run our code from here. So instead of having to watch it do the whole thing again, we can actually place our rover in a specific location on our map here, and off we go. Now, this little red square is thrown as a miss because what we did with our little change before was, if we were driving forward last, then we just keep driving forward, so obviously we just drove straight off the edge. So what we could do here is go and add another else if, and what I would normally do in this case is look for our red on our left sensor. So I'm just again going to back this guy up to here. I'm just going to run that program again, but while I'm watching this sensor view, because I want to see if we actually detect red, which we do. So that's great. What we can do now is we can go in and add an additional case for if the right sensor is red. What do we want to do? In this case, we probably just want to turn right. We probably want to turn right by 90 degrees, and we might have to tune this in, because what we want to make sure that happens is that our sensor then gets back onto the line. So same deal, I'm just going to back our robot up here, run this one. We'll see we didn't actually trigger that last case. So let's see if we do it again, whether it will.
Look, what you're doing in class, there's a square, it's like 70 minutes nearly to start with, and then you're going.
Yeah.
Yeah. And he might. Here we go, here we go, here we go, here we go. There we go. Oh no.
Oh, hang on. Here we go.
You want to specify what? He's zoomed in on the.
Yeah.
Hyper rapidly.
Do you want both? We can do both.
There you go. Alright.
Granted, I just tested this and it didn't quite work, but it's close. All good?
The only thing he doesn't have is the color value. No, I've got a photo.
Ah, cool. What do you mean with the color value there, Harvey?
Oh, you got me on the. Sorry.
I can hear you,
Yeah. We just can't view the middle color value. It's just coming up white.
Yeah, so that's right. So what we've actually got is in there is that color piece.
Oh.
Yeah. So rather than using the one you're probably used to is this guy here, which is like basically the value, right? So rather than you might go in here for the red, you might go and pull the number. And when you do that, what you're going to end up needing is this comparison like we had before. So this is good. This is another way we could do the red.
Yeah.
So we can say if the red from the right sensor is greater than, and let's just quickly check a number. We roll this back. We're getting red as 255. Problem here, what we get is that red on white is also a pretty high number.
Yeah, because we had this
really
issue.
Tricky. And so in that case, what you sometimes need is to let me just throw this into another program just so I can test it out.
what we can do is, if the hue from the middle sensor is, we're going to go red, we're going to go right, is less than, sorry, we want to go greater than 2, let's go 230. I'm just going to put in here a print that says is red. And,
I'm just in a moment. Yeah, that's right. I'm just going to put date.
So we should then get is red comes through. But if I now go and place that robot on the white line, so let's just do this, where we get all 3 sensors on the white. See, they all go 2 for 5, so we're still going to get is red. What we can do is, and this is getting a bit more complex, is add an AND. So now we're saying, let's just make this box. Now what we can do is say, if it's red but not blue, then we say is red. So now we'll get not is red. If I put it on the red, I can do it over here, drop this back on the red, we'll get red. And so basically that is the more complex version. Like, that's the manual way of doing what we've got in our software as this block. But what you can also do is, if you need something that's if you've got say you've got red tape, I've only got black tape here, but say you've got tape that's not quite red, it's orange or something, and you just would rather not have to deal with, tuning this in. What you can do is pull in, there's another version of this that says within range.
I'm at GD at the moment. Can I give you a call back in a little bit?
And that'll actually give you the ability to set
Sounds
the
good.
degrees of
Not
the
a problem.
wheel.
Bye.
So you can then say, well, is it red within a range of a big number? And so I can set that to 50, and it'll pick up yellow and orange probably as well. Remembering that these colours that are coming through are, when we're talking about hue, I'm just going to pull this up because it's the easiest way to explain it. We're talking about hue, we're talking about the colour wheel, and so we're saying that a hue of 0 at the top here is red, and as we go around the wheel, it's, green is 180, blue is 270, orange is 90. And so we're looking at that 50 is saying within 50 degrees of red. So 50 degrees of red means we end up sort of pink and orange as well, covered. Whereas if we set this to really, really fine, if we say 3, then we're looking for a really, really, really specific red, which in the simulator will work great, because the hue in the simulator is getting 354 for red, which is, out of 356, so it's pretty close. So we could say within 4, and that would work. But in real life, if you've got red sticky tape or red electrical tape or whatever you're using, your red might be 90 degrees different to red. And so that within range block is useful as well.
Cool. No, thank you. Yep.
Awesome. So we also got a question, could you show how the robot to continue from a certain point again? Yep, absolutely. So in our simulator, up in this menu, so the same place you go to change exercises, so you jump back into change an exercise, there's a tick box here that says reset rover on play. And what that does is as soon as you run your code, it puts it back in the starting position. There is also a separate reset button here. So if you're mid-program, like if I'm running my program and I just want to go back to the start and continue, I can just hit reset without stopping the program. It'll go back to the start. And what you can also then do is uncheck that one and check keyboard controls. You can then use the keyboard to get your rover into position where you need it. So we can say, all right, we know we can follow the line. I just want to make sure that we can do this roundabout. And so I can just place our robot in here and we can run our code. Off we go. Awesome. Were there any other questions? No, all good. Awesome. All right, yeah, so I'm not going to go too much further into this because I just realised we're running out of time. And so
you're welcome, as I said, your accounts will remain active for a month after the session, so you can play around with this, see if you can get the line following course completed with the little red circles, because it is a bit tricky. The other option you've got here, rather than detecting the red, is actually just detecting a T intersection. So you'll see that when you're right on the edge of that line, you'll get all three sensors of white. And so the same as what I was just showing Harvey, you can use this AND block to actually say if the middle sensor is white and the left sensor is white and the right sensor is white, then we know that we're at this T intersection. Unfortunately, though, that won't work over this side, so you have to do something different for this area here. Otherwise, you'll just end up doing loops of the circle, which is why the red dots are there in the first place. Sweet. Yeah. So as with the balancing challenge, there are a whole heap of different versions of this. Obviously, the easiest version is to use a single sensor rather than using three. The medium version, which we just did a little bit of, is using all three sensors, so we're using that to do our turning. But line following is a challenge that is run all around the world as a competition, and so there's a whole heap of different things you can do. Obviously, we can add our little red squares for our corners that we want to do. We can add obstacles on the line to avoid. So use something like a water bottle works really well. Just put it on the line so that when they move up to it, they have to actually navigate around it, return to the line, keep going. You can add different coloured lines to denote how fast they have to go. So there's certain sections that have to be faster than others. You can use variables and stuff to make our code easier, and obviously we can go and enter in these competitions, which can be really fun. So just finishing up, I just wanted to show you really quickly the other challenges that are available in the simulator, because as I've said a couple of times, you do have access to this now. You can have a play around. I'll show you a few of my favourite ones. This is one of them. This is one that we call drawing shapes. So we had driving shapes that we did as our first little exercise, and we also have drawing shapes, which is this one here. That allows you to actually have a whiteboard marker on the back of your rover and drive around. Spike drop is really fun. It has some spikes here, and you've got to use either the color sensor or the ultrasonic distance sensor on the front to stop in this green region, because if you don't, you get land on the spikes. We've got line following, which we just did. There are a couple here in the middle that are impossible to do in real life, like the half pipe. I shouldn't say impossible, you could probably build one of these, but what this does is actually uses the gyroscope to basically do swishes back and forth on our half pipe. We've got the invisible bridge. This one you couldn't do in real life. Is a maze that you actually can't see, so you can make sure that students are doing it with sensors, because they can't see where the actual maze is. We've got the seesaw, which we covered. We've got the balance board, which we covered. The maze is really cool because the maze lets you generate an infinite sized maze. So you can have infinite possibilities of this maze. You just keep generating them for students to do. And then when they finish the hardest square mazes, there are also hexagonal mazes and triangular mazes that work really well as well, really hard. Another really cool one is we have a sumo battle arena where you can battle another artificial intelligence robot. There are 3 levels of difficulty. El Capitan is reasonably hard, but you can also add some of our 3D printed attachments to your virtual rovers so that you can simulate those as well. The last couple, driving school. Driving school is a really cool assignment challenge. It's basically a simulated town where you've got to navigate and avoid other rovers. In the middle here you've got traffic lights that are the colour sensors. You've got a pedestrian crossing with a duck on it. You've got to not run into the duck. So you see this blue car here, and we'll now move along. And the last one was a partnership we did with the Crossover Rail up in here in Queensland. Basically, it's a set of train stations that all have a programming challenge at them, where you have to take duck passengers all the way from the first station of the tunnel to the last station of the tunnel. Yeah, it's a really cool little challenge, and you can also then send students on specific little challenges. Awesome. So that is all the content we had covered. If there are any more questions, more than happy to answer them now. Otherwise, you do have our contact details. You can shoot us an email. But if there are any questions, feel free to jump in. please get in touch with any feedback you might have around the sessions and the communications leading up to it. As I said, your accounts remain active for a month, so you can keep playing along and try some of these challenges yourself. We've also got it's in about a month, another one of these webinars around 3D printing. A lot of it is around how to get the most out of your 3D printers that you've got at your school, as well as a few examples of how you can use them with the rovers to do more and more advanced challenges, as well as getting into some of the attachment stuff that there was a question about earlier. So yeah, we encourage you to join in on that one as well. So we've got a couple of questions. Nicole said, I use DuckyTown for assessment, which is great. Yeah, it's a really good assessment piece because it does have that sort of lead-in of there's a whole heap of different challenges you can do. So it's pretty easy to then sort of assess it piecewise as well. Max has asked the question of, can I limit what exercises the students can see? Assuming in the simulator, at the moment you can't, but it's actually a really cool idea. At the moment they can see all of them, and we do get students who just fly through all of them immediately. It would be really interesting to be able to say, yeah, you can only do these 3, and then release them progressively. So we might have to think about how we can do that one. So I actually would quite like that idea. If there's not any other questions, I'm more than happy people to start heading off and enjoying your evenings.
I got one more question.
Yep.
I saw that you had a connector for like a dump truck with a.
Yep.
What's the connection to the physical Micromelon from that to? There's one where it actually lifts. It has a lifter on it.
So, sure. So the way that it actually works is quite cool and hidden. There are on the robot these little divots. So you can see that little. It's kind of hard to see on camera. It's a little divot.
Yeah.
What we have at each of these attachments clip on with something, usually a modified version of this. I'll pull that up. Of this. So this actually has those little divots in it. And so they actually clip on to the robots without screws or anything. So they actually clip on to the robots, which makes it really useful. So students can build up on top of one of these. So which makes it really useful. So students can build up on top of one of these. So what we quite often see is students or just grab this and then start designing, and then they just clip them off their robot, or just grab them ones off the side, and then they just clip them off their robot and put them. And so they don't have to keep locker or in the desk. They don't have a robot physically allocated. So they don't have to keep the entire time. They don't have a robot physically allocated to them the entire time. So what you'll see is that one that you're talking about, which I think is the. So what you'll see
little dump truck which has a little little digger. So yeah, has the sensor on the top. No, it's not a sensor. Little motor on top.
Motor, yeah. So you see that just clips onto the front into those little divots. The motor, yeah. So
yeah. Where does the motor connect to on the actual unit?
So the motor on the robot itself, we have. Sure. So the motor on the robot itself, we have. So you can add 2 servo motor connectors, standard servo motors straight onto. So you can add 2 standard servo motors straight onto the Micromelon rover, and then in the editor is still programmable in the editor. In the extensions category, you've got set servo degrees and move left servo. So you can just bring these in like normal code, and that'll control those extra motors that you've got on the back of the robot.
And it's sensor left, sensor. Is it like left and right? Like
yes, So you've got one left, one right, one.
Gotcha.
On the robot, so.
Excellent. Okay, thank you.
No worries. Awesome. Oh well, if there aren't any other questions, thank you very much for coming around. Yeah, have a good evening, guys. Cheers.